Hello everyone, this is Ann Lemaster. What we're going to be talking about today is the urinary system. And when you think about the urinary system, one of the things you're thinking about is removal of metabolic waste. There's a few more things it does, and we'll talk about those in a moment. But first we're going to talk about the parts of the urinary system. There is 2 kidneys, 2 ureters. These are the tubes that lead from the kidney to the urinary bladder. And then from the bladder, you lead to the urethra and out. And on the picture on the right is the one I like best, so that's the one I'm going to go over. Here they're kind of greenish. These are the kidneys. In red, you have the ureters. Now this part here is still the kidney. It's referred to as the renal pelvis, but again, this is where urine is formed in the kidney. It's going to be draining down the ureter to the urinary bladder, and again, out the urethra. Okay, what does the kidney do? Well, it does a whole lot. It regulates ionic compositions, regulates sodium, potassium, calcium and chloride and phosphate ions, regulates blood pH, so hydrogen ions as well, osmolarity, which is talking about how much solute and water are in the blood, and glucose, regulates blood volume, and that conserves or eliminates water, because remember, the serum of the blood is 90+% water. And because it can regulate blood volume, it can also regulate blood pressure. The higher the volume of blood, the greater the pressure. It does that in a couple ways. It secretes the enzyme renin. Renin leads to the angiotensin 1 and 2 and aldosterone. And also it can adjust renal resistance, meaning it can change shape it can constrict the blood vessels leading into the kidneys. Okay, the kidney also releases erythropoietin, which is necessary for formation of red blood cells, and calcitriol. That is going to help with the absorption of calcium. And of course, there is excretion of waste and foreign substances. Blood supply. At any one time, even though the kidneys are small, they have about 20 to 25% of the resting cardiac output. So they get a lot of the volume of the blood. And renal nerves are innervated in parts by the sympathetic portion of the nervous system, sympathetic branch of the autonomic nervous system. There we go. And mostly what that's going to regulate is blood flow into the kidneys. Now the nephron, which is here, again I'm on the right, this is the functional unit of the kidney, and each nephron receives one afferent arteriole. Again, afferent means going towards something. And in this case, the afferent arteriole is going to a special capillary ball called the glomerulus. Now this capillary ball is unique because what leaves the glomerulus is another arteriole, this time efferent, meaning leaving. It divides to form the peritubular capillaries. These are the capillaries where bulk flow occurs and nutrient exchange. What would happen in a normal capillary. And some have a vasa recta. And moving to the right here, the vasa recta is this part. This is only found in a special type of nephron. We'll talk about that in a minute. And it does play the same part. It does deliver nutrients, but it doesn't disrupt the osmolarity, and we'll talk about why that's important in a bit. So here is the afferent arteriole. Here's the glomerular capillaries, efferent arteriole, peritubular capillaries, and some happen to have a vasa recta, and they lead to the veins and out the kidney. Okay, here's my mouse. Functions of the capillary beds. So up here is the peritubular capillaries, and notice it goes from arterial end to venous end. So this is going to provide nutrients and carry away or reabsorb substances. Here at the bottom is the glomerular capillaries. At the afferent arteriole and efferent arteriole. Their job is primarily what's called filtration. And when you filter, you kind of push things through. So this is where substances are going to leave the blood, leave the capillaries, and enter the renal system, particularly the glomerular capsule, that part of the nephron. Now let's talk more about the structure of the nephron. Each kidney has about 1 million nephrons, and there's two parts: the corpuscle, which is the glomerulus, which is the capillary ball, and that is right here. And then you have something called the Bowman's or glomerular capsule, which is here. So the glomerulus, again, part of the cardiovascular system. It's because it's arterial. And then here you are getting to the first functional part of the renal system or urinary system. Here's another view of the nephron. Again, this is the glomerular part, and most of the time I'll call that the glomerulus, the capsule, plus the glomerular capillaries. The rest is the renal tubule that contains the proximal convoluted tubule, proximal being near the glomerulus, the nephron loop, and you have a descending and ascending, the distal convoluted tubule, and this will go into collecting ducts, and these collecting ducts will lead through the calyces into the renal pelvis, and of course from the renal pelvis out the ureters. Now there are two types of nephrons. The first type is cortical. Cortical meaning, when you see the word cortex, that usually means the outer part. So the cortical, most of the nephron is located in what's considered the cortex of the kidney. And about 80+%, 80–85% of your nephrons are considered cortical. So, okay. The other 15–20% are juxtamedullary, and the medullary is the middle part. So what differs here is, okay, you might be able to see that, but I can't. Okay, is how long the loop of Henle is. And notice how far down the loop of Henle goes into the to the medulla of the kidney. These are special neurons, juxtamedullary nephrons, because these are going to help you make more concentrated urine, and we'll talk about that toward the end of this lecture. Okay, the histology. So the tissues that make up the glomerulus. So the glomerular capsule consist of our friends parietal and visceral. Visceral are the simple squamous, and they have podocytes. So if you look at them, they look like they got little feet, or pedicles. And then the parietal layer is this layer, and it forms a capsule. And this is where fluid is going to enter from the glomerular capillaries. So notice it's a very thin layer of cells, just one cell layer thick. Very good for diffusion. The proximal convoluted tubules and others, well, the proximal convoluted tubules have microvilli. Microvilli increase surface area, and increase in surface area is excellent for absorption. Loop of Henle, simple squamous and cuboidal. And in the distal convoluted tubule and collecting duct, you do have special cells that are that contain receptors for antidiuretic hormone and aldosterone. And if you remember, both of these increase the reabsorption of sodium, which increases the reabsorption of water. So it makes you retain water. And you also have some intercalated cells which help play a role in pH, which is another function of the kidney. Another portion of the kidney is called the juxtamedullary apparatus. And it is located, if we look here on the right, where the ascending loop of Henle, so this is the loop of the nephron that's going upward, makes contact with the afferent arteriole of the glomerular capsule. And right here, and here, you have what's called the macula densa. These are thickening of cells. And then here you have some juxtaglomerular cells. And what these are going to do is kind of regulate the size of the arterioles. So they're going to regulate the blood pressure, or the pressure of the fluids flowing into the nephron. All right, so that's the anatomy and histology. Now we're going to talk about physiology and the 3 steps needed for urine formation. So urine is a product of 3 processes. Glomerular filtration. And basically, glomerular filtration is when fluids leave the glomerular capillaries and enter the glomerular capsule. So they enter the nephron. Tubular reabsorption occurs in the tubule area of the nephron, and fluids leave the nephron and re-enter the capillaries. And the last step is tubular secretion. And I like to think about that as a fine-tuning of the urine. This is where ions and waste, like drug metabolites, re-enter the nephron to become part of the urine. And this is kind of a brief overview of what I just said. In glomerular filtration, water and most solutes move across the wall of the capillaries and into the glomerular capsule. From the glomerular capsule, they enter the renal tubule, and tubular reabsorption occurs. And the fluid moves along the tubule and is reabsorbed back into the blood. So you'll notice here 99% of what is filtered in the glomerular capsule is reabsorbed in tubular reabsorption. And lastly, Tubular secretion is when other fluids, such as waste and drugs, re-enter the nephron. So you're removing these substances from the blood and kind of fine-tuning the urine, if you will. And then everything that drains into the all the solutes and waters that drain into the renal pelvis remain in the fluid until they're excreted. And filtration plus secretion minus reabsorption. That's the equation for excretion of any solute. So let me see. Let me do this here. Okay. Here we go. And here's another way to say what I've said in the past couple of slides. So here are the capillaries in red, and then in the yellow you have the nephron. And what this is showing you is which way fluids are flowing. So in the glomerular capsule, fluids are flowing from the blood into the nephron. In tubular reabsorption, fluids are flowing from the tubule into the blood. And then tubular secretion, things are flowing from the blood into the nephron. Okay. Now, glomerular filtrate. I know there's a lot of words on this slide, but what I want to focus on is this part right here. Your daily volume between 150 and 180 liters are filtered. So your blood is filtered several times a day. You only have about 5 liters of blood. So during the day, your blood is filtered a lot. And this is why 99% of that blood plasma is returned. Or in other words, the fluid, 99% of this leaves the nephron and is returned into the bloodstream. In other words, you only urinate about 2 liters per day, even though you filter about 180 liters. And here it is in handy chart form. So even though you filter this much fluid, you only lose about this much fluid once the fluid has traveled throughout the whole nephron. Now, what drives the fluid to move? With all of our other systems, it has been pressure, and the urinary system is no exception. You have several pressures. The main one is the glomerular hydrostatic pressure. This is driven by heartbeat, and again, this wants to push blood from the capillary into the nephron. 2 pressures oppose this. The first one is the plasma colloid osmotic pressure. If you remember, colloids are large proteins that can't leave the bloodstream, so they want to pull fluid into the capillary. You also have pressure inside the capsule. This is capsular hydrostatic pressure, and this is going to push fluid from the capsule back into the capillary. And you have a net filtration pressure. This is small, but it wants to push fluids from the capillary into the nephron. So things move from higher to lower pressure, and usually the highest pressures favor fluids flowing out. And again, this is in the glomerular area of the nephron. So filtration occurs in that area. Glomerular filtration rate is the amount of filtrate formed in both kidneys each minute. Homeostasis, that internal balance, requires the kidney maintain a relative constant glomerular filtration rate. If there's too high, if the glomerular filtration rate is too high, substances pass into the nephron quickly and are not reabsorbed. If it's too low, then everything is almost reabsorbed, so there's not adequate secretion or excretion. So there's two ways to regulate glomerular filtration rate. One way is to adjust the blood flow in and out of the glomerulus, and another is to adjust surface area available for filtration. Okay. Excuse me. All right. So here are some mechanisms regulating glomerular filtration rate. The first one is renal autoregulation. And that means the kidney itself is regulating glomerular filtration rate. There's two ways. Myogenic mechanism. So this refers to muscles, and this is the muscle of the smooth muscle in the afferent arteriole. So occurs when stretching triggers contraction of the smooth muscle in the afferent arteriole. So that's going to reduce glomerular filtration rate. Tubuloglomerular mechanism, this is our macula densa, provides feedback and inhibits the release of nitrous oxide. And by inhibiting that, it's going to cause the afferent arterioles to constrict and decrease the glomerular filtration rate. The nervous system, also particularly the autonomic nervous system and the sympathetic branch, affects glomerular filtration rate. Moderate stimulation causes both the afferent and efferent arterioles to constrict, and glomerular filtration rate decreases. Greater stimulation constricts the afferent arteriole, and the glomerular filtration rate drops. Other ways that the glomerular filtration rate is regulated is through hormones. We have angiotensin II. It reduces the glomerular filtration rate because it's a potent vasoconstrictor of both the afferent and efferent arterioles. Atrial natriuretic peptide, ANP, increases glomerular filtration. It stretches, it increases capillary surface area for filtration. So this is one of the few that actually are not regulating blood flow but increasing surface area. Okay. One thing I did forget to mention, and I'm just going to talk about the afferent and efferent arterioles. The afferent arteriole leading to the glomerular capillaries is larger than the efferent arteriole. So that's always going to keep blood pressure kind of high to the glomerular capillaries. Okay. Tubular reabsorption. So as substances move into the renal tubules, they are reabsorbed into the peritubular capillaries. And most reabsorption, about 70%, occurs in the proximal convoluted tubule. Remember, it's lined with microvilli. More microvilli, greater surface area, more reabsorption. Okay. Now, what are some of the mechanisms of reabsorption? Well, you have active transport. Remember, ATP is used. This is for glucose, amino acids, certain ions. The one we're going to talk about in particular is sodium. Sodium ions are actively transported out of the nephron. Water is reabsorbed via osmosis. Remember, this is passive. Osmosis is just going from higher to lower concentration. And small proteins that have a little bit of molecular weight are reabsorbed via endocytosis. Okay. Water and sodium and water reabsorption. One way to remember this is that water follows salt. So again, water reabsorption is passive and is associated with the active reabsorption of sodium ions. In other words, whichever way the sodium ions flow, water is going to follow. Okay. All right. And notice here at the bottom, even though you filter and reabsorb a lot, you don't excrete a lot of either water or sodium. Tubular secretion, the mechanisms that drive that. Again, tubular secretion is when molecules re-enter the nephron from the capillaries. Active transport is the main mechanism of function here. And again, what's usually secreted? Drugs and ions, particularly hydrogen ions. And this is tubular secretion is very important in regulating the pH of body fluids. And that's what this slide is showing. This is secretion here, and hydrogen ions are being returned to the nephron, which is in yellow. Okay. All right. Hormones also affect tubular reabsorption and tubular secretion. Angiotensin, in addition to decreasing filtration, can enhance the reabsorption of sodium chloride ions in the PCT, proximal convoluted tubule. Aldosterone can stimulate cells to reabsorb more sodium and more chloride ions and secrete potassium. Usually what that means is sodium, when sodium goes one way, potassium goes in the opposite direction. Kind of keep in mind the sodium-potassium pump. And parathyroid hormones stimulates the reabsorption of more calcium, helping to keep your calcium ion or calcium levels in check. Antidiuretic hormone or vasopressin. This increases water permeability in the latter parts of the nephron, particularly the distal convoluted tubule and collecting duct. Normally these are not permeable to water, and we'll talk about that in a moment. Atrial natriuretic peptide. This wants to increase blood volume, so it's going to, or decrease blood volume, I'm sorry, by inhibiting reabsorption of sodium, and it's going to inhibit water reabsorption in the proximal convoluted tubule and collecting duct by suppressing antidiuretic hormone and aldosterone. So ANP does the opposite of aldosterone and antidiuretic hormone. Okay. So when you make concentrated versus dilute urine, same three processes apply. What differs here, well, the type of nephron, but what we're going to talk about here is some differences, some subtle differences in the loop of the nephron. This is the descending loop, and the descending loop is permeable to water only. And if you remember, water is passively transported via osmosis out, okay, back into the capillaries. Here in the ascending loop, these are not permeable to water, but sodium and chloride ions are being actively transported out. So the more the sodium and chloride are transported out, the more sodium and chloride are in the fluid around, particularly the descending limb. So the more sodium and chloride there, the more water will be passively transported out via osmosis. And this is referred to as the countercurrent mechanism. It's called the countercurrent mechanism because of the flow of the water, of the fluids in the nephron. They're flowing down and then they're flowing up. Okay. I think the next slide is a little bit better. And here in the glomerular or juxtamedullary nephrons, what we're going to show you is how, or what the slide is showing you is how dilute urine is made. Dilute urine is very watery urine. Okay, so we're in the nephron. Glomerular filtration has occurred, and now we're going to the proximal convoluted tubule and the descending loop of Henle. And remember, the descending loop of Henle is where water is being passively pumped out. So it's passively removed. So as you go down the loop of the nephron, notice that the sodium concentration outside of that is higher. This is important because the higher this goes, the higher the concentration of sodium on the outside, the more water is going to be pumped out. So you get a very concentrated urine when you reach the bottom of the loop of Henle or the bottom of the loop of the nephron. However, as you come up the loop of the nephron, what's occurring is the active transport of sodium and chloride. So sodium and chloride are being actively transported out. And as they become actively transported out, your urine becomes more and more dilute. Now remember here, once you get to the distal convoluted tubule and the collecting duct, they are impermeable to water. And again, only ions can be removed. So by the time they reach the collecting duct, you have a very dilute urine. Now, to produce a very concentrated urine, meaning a urine with lots of solutes, what has to happen is that the distal convoluted tubule and the collecting duct have to become permeable to water. If they do become permeable to water, water will flow out passively from higher concentration than the collecting duct to lower concentration in the solutes around the nephron. So this is where antidiuretic hormone comes in. Antidiuretic hormone actually pokes holes or introduces aquaporins, and so the water passively comes out. So this leads to a very concentrated urine. Okay. Urine composition. Let's see. Urine is about 95% water, and I'm trying to find my mouse here. The primary waste products are urea, uric acid, and creatinine. These are metabolites of amino acid degradation. Remember, amino acids have the amino group, and the amino groups form these. Also, other amino acids, some electrolytes, and again, lots of things can affect urine composition. And I believe this is our last slide here. And in the last slide, we have the colors of urine. I found this on the internet, so it must be true, but I think it's kind of cool. Normally, you have urine somewhere in this, maybe here if it's really concentrated. But urine can come in all sorts of colors. That is not usually good. This is not usually good either. It's cloudy. That means you may have a type of infection. Red urine usually means there's blood in the urine, or you've eaten a lot of beets. Brown can mean bilirubin, could be suffering from liver cancer. Orange could be medications turning your urine orange. Yellow is the normal color. The darker the yellow, that could be a sign of dehydration. Green could be caused by infections, but it's due to blue urine, and that's due to genetic variation. Also, some medications can turn your urine blue, and violet indicates kidney failure. Now with this, I'm going to recommend, if you have an unusual color urine, to see a physician and not Dr. Lemaster, because she just has PhD. Anyway, I hope you enjoyed this, and I'll chat with you guys later. See you next week.